Chapter 2 is the beginning of geometric proofs, and as we move into geometric proofs, there are a lot of properties and theorems and postulates that you need to know in order to complete a proof. We will begin today with just an introduction to proofs with some algebraic proofs that you may have seen last year in algebra. But before we can begin that, we need to define some of these words on our Cornell Notes sheet. Postulate is the first word. A postulate is a statement that describes a fundamental relationship in geometry. We have talked about, or will talk about, a linear pair postulate. It's a very popular postulate. So we'll put that here for now so we can use that as an example of what that postulate is. Second, we have a theorem. A theorem is like a theory. It comes from the same word that theory comes from, but it has been proven to be true. So you can think about it being a theory, but someone took that theory and then proved it to be true every single time. So it's a conjecture or a theory. A conjecture is just like a theory or thought. A conjecture that has been proven to be true. And an example of this is the vertical angles theorem, which we often will say vertical angles are congruent instead of writing out the entire theorem. But that's the vertical angles theorem. So a theorem can be proven to be true, and a postulate is a little more basic. You can look at a picture and know that two angles add up to a line, like the linear pair postulate. Okay? Now, as we move into a proof is just a logical argument where each step is supported by a reason. A logical argument where each step is supported by a reason. Okay? And when you set up a proof, you make a table. Your statements go here on the left side. Your reasons go here on the right side. So on the right side, we'd be putting our postulates. We'd be using our theorems. We would be using lots of definitions and things like that to state why the things on the left are true. And then at the end of the proof on the right side would be what you were trying to prove. But we'll get into that more as we move into algebraic proofs later on in the section. Now, there are some properties that we need to be familiar with. You may have learned them in pre-algebra or in 8th grade math. You may have not. The first one is called the reflexive property. What do you think of when you hear the word reflexive? You're thinking of reflection, probably. And that's a great way to think about it, because reflexive property says that angle A is congruent to angle A. And that seems silly that you would have to state that an angle or that anything is congruent or equal to itself. But when we're working in proofs, we may have to use this step. We actually use this step often. Reflexive property could also be the measure of angle 1 equals the measure of angle 1. So if you're doing angles are pictures, so they are congruent. Pictures are congruent. If you're saying a measure, the measure of this angle, and you want to say they're equal, then you would have to use an equal sign, because the measure is a number. The measure of this angle is equal to the measure of this angle. So you want to think about your reflection in the mirror because it looks exactly the same. All right, you don't stand in front of the mirror with a green dress on and see yourself in a red dress. So reflexive should be pretty easy. It's exactly the same on both sides. Now, reflexive property can be confused sometimes with the symmetric property if you're not thinking about it the right way. Think symmetric comes from the word symmetry. Symmetry. That's the word you're thinking of. They come from the same root. And think about what symmetry means. All right, something like a heart has symmetry because you can draw a dotted line down the middle and flip it over or fold it over on itself and it'd be the same on both sides. So this is what I want you to think about. You could flip it over onto itself and then both sides would be exactly the same. Okay, so if we think about that in the symmetric property, then it would say if the measure of angle ABC is equal to the measure of angle DBC, then flip this over. The measure of angle DBC is equal to the measure of angle ABC. So all you are doing is flipping the left side with the right side this is the hypothesis, which we'll get to. In the if portion of the statement, you take whatever the equality is and you flip it over. So symmetric, think of symmetry, think of a heart, folding it or flipping it over on itself. So you flip this. We do this a lot when we solve an equation. You don't have to write this down. I'm just going to write this down to show you. When we solve an inequality, we might get 3 is less than x, like this. And if you want to put it in set notation, remember the x had to be on the left side. So we put the x on the left side, the 3 on the right side, and we flip the inequality symbol so we could put it in set notation. You should have done that in algebra last year probably. So sometimes it's just required that a certain piece be on the left side, like in this case, or a certain piece be on the right side. So you just take that statement and you flip it over. It's still going to be true no matter which way you write it. Like red is a color is red, or the color is red. So you're just flipping it over. Still ends up being true. The next one is actually my all-time favorite property, the transitive property. Several years ago, there was a commercial on TV for Everybody Loves Raymond, that show, and it said, "Everybody loves Raymond. Raymond is on Wednesday nights. Therefore, everybody loves Wednesday nights." So it said that, I'm going to put it this way, everybody loves Raymond. And then it said, Raymond is on Wednesday nights. Therefore, everybody loves Wednesday nights. Okay, so there's a shortened version of that. Okay, what the transitive property does. Now, what you want to think about is what trans means. There are a lot of words that trans is a part of. Transcontinental Railroad, transmitter, some others, transition, okay? Trans means across, So when you think of trans, you want to think of reaching across the link. For instance, if everybody loves Raymond and Raymond is on Wednesday nights, the link between these two statements is Raymond. So what we do is we reach across the link. So these two link the statements together, the Raymonds. You reach across the link, and that's how we can link everybody loving Wednesday nights. So let me put this in math terms for you. If we had a statement that says, if angle A, I should write the measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then the measure of angle A equals the measure of angle C. Now, some would argue that this should be congruent. So transitive is usually only congruence. I put it in equals here. But if it says if the measure of angle A is equal to the measure of angle B, and the measure of angle B is equal to the measure of angle C, let's go ahead and change this to congruence. If angle A is congruent to angle B, if angle B is congruent to angle C, then angle A is congruent to angle C. All right, so we want to, let's save transitive for congruence only. Okay. Now the link in this case from the first statement to the next statement is what do they have in common? They've got a B in common. So B is the link. You reach across the link from A to C, and then you can link those two together. So B is the commonality. You reach across that link, and you can say that angle A is congruent to angle C. Transitive. One more example of that. If Bowling Green beats Maumee in football, and if Perrysburg beats Maumee, and Maumee beats Bowling Green, then we could probably assume that Perrysburg will probably beat Bowling Green. So it's a thought process we have to go through. We actually do this often with sports, but we've never probably written it down on paper. So find the link between them, reach across the link to say the first is congruent to the last. All right, the last property we're going to talk about today is the substitution property. Now, if transitive is only congruence, substitution is only equality. We only use it for equality. And we use substitution property in algebra all the time. When you take something that's equal to something else and you plug it in place of it. So there's two times when you call it substitution property. When you're plugging something in, okay, and I'll give you an example of that. If it says if A equals 3, then 3A plus 5 is equal to 3 times 3 plus 5. So when we rewrite the statement and we take the A equals 3 and we just plug it in place of it, then that's substitution. Okay? So that's plugging it in. You're plugging it in for something that it's equal to. So instead of A, since A is equal to 3, we put a 3 in place of A. That's your first version. The second version is anytime you combine like terms. Now this we will only see, we'll see in our algebraic proofs, but we won't see so much in our geometric proofs, maybe a couple times. But when you combine like terms, for example, if A plus A equals 16, then 2A equals 16. So we know that A plus A equals 2A. So since we know that to be true, we can go ahead and combine those like terms to write 2A. We're still putting something in place of something else that it's equal to. So it's the same idea. There's just two different ways that you can see it. All right. So these are the properties that we're going to be using. And, ouch, let's look over at our notes here then for section 2.5 and 2.6, properties and intro to proofs. All right. What I would like you to do is, using the properties I just gave you, I would like you to pause here and do problems 1 through 10 on your own and see if you can figure out each of the properties.